Welcome back, everybody. Let's continue with this. Also, before I continue, I would like to say I am configurable. You can accelerate me, you can slow me down. So I will ask, at the end every time to check if you're following or not. But I can adapt my speed, right? If you want me to go faster, I can go faster and throw in more material for the exam. If you want me to go slower, I can go slower. So I can really adapt to you. So don't hesitate to give me feedback, especially at the end when I ask. All right, so we've seen the integers, we've seen the arbitrary precision decimals, but there is something else. Because these arbitrary precisions that I showed you, especially with the precision and scale, when you have a fixed scale, like for monetary amounts, for example, 2 digits after the comma is common, this is called fixed point decimals, because the decimal period is always at the same place, right? But there is something, especially when you do, I don't know, for physics and certain applications, you might be dealing with numbers with all kinds of powers of 10, right? Maybe for some numbers, you're talking about, I don't know, attoseconds, like those who got the Nobel Prize in a few days ago. Attoseconds, it's 10 to the power of minus 18, I think. And basically, you need a lot of zeros before you have your first digits, right? And on the other hand, you might want to express the weight of Jupiter, the planet. And in fact, the weight of Jupiter broke the scale of prefixes because there are too many digits, and they had to add these 2 new prefixes for 27 and 30 zeros, right? So if you want to both be able to store durations in attoseconds and at the same time the weight of Jupiter, then you realize that fixed point doesn't work. You need something that is floating. So this is what we call floating point decimals, where the decimal period can be anywhere. And the trick for doing that is the scientific notation. You might have heard of the scientific notation. Is basically you take a number and then you look at the first digits and look at what power of 10 this is. Like, for example, if you have like 1,024, then you're going to rewrite this as 1.024 times 1,000, 10 to the power of 3. This is called the scientific notation. And that's the trick. Then you store separately all of the digits. It's called the mantissa, correct? And then you have the power of 10 that follows, and the power of 10 plus the mantissa gives you enough information to reconstruct the number. So this is the idea for storing the decimal numbers in a floating point convention. But of course, you might know that computer scientists, they prefer powers of 2 because it's much more geeky to deal with powers of 2, and it's the bits of the computer. So we do the same, the scientific notation, but we use powers of 2. So instead of powers of 10, but it's the same idea, right? So in that case, I just realized that this number right there, that is quite long, is actually this in base 10 times 2 to the power of 31. And what you do then is that you store the power of 2 separately from the mantissa, right? So technically, this 31, the power right there, it goes in here, in that slot. And then the mantissa goes there, even though you remove, in base 2, here it's base 10, but if you convert that to base 2, the first digit is always going to be a 0, because that's base, or 1, no, it's a 1, always a 1. And then you can omit the 1 in there. You save yourself 1 bit. All right, and this is always fixed. So you have a fixed number of bits for the power of 2 and a fixed number of bits for the mantissa, and 1 bit here for the sign, plus, minus. And so you see, you can squeeze all of these numbers here like this. But of course, this here is limited to a specific size. So what's going to happen, it's why it's called approximation of real numbers, is that you might cut after a couple of digits, all the rest is lost, and you just squeeze as many digits or bits as you can in there, right? And that's why if you actually try to store numbers like that, you might be in for a small surprise like this, that when you read it back, it changed a little bit here, but that has to do with the fact that you have to truncate in here, right? So that's the idea. And there is a standard for that that's called IEEE 754. And don't ask me why I can actually remember that. I have no idea, but this is the name of the standard. And it has 2 different flavors, one on 32 bits and one on 64 bits. In fact, it has many more flavors that you can adapt the features, but overall, this is how it works. This is what is commonly called, if you remember in Java, there's float and double. Well, float is the one on the left, and double is the one on the right. Double because of double precision, because we double the number of bits. And why 32 and 64? Well, that's because it's the size of the registers. That's the size of the registers in the processor on the computer. So that's why. Now, I'm giving you just the intuition that on the float, on the single precision floats, it's roughly 7 digits of precision. And anything beyond 7 digits is going to be lost. While for 64 bits, it's 15 digits of precision, and then the rest is lost. The powers of 10 are also a bit different because on the 64 bits, the size of the power is also slightly bigger. So you can actually go with the single precision 10 to the power of 37 to 10 minus 37 to plus 37. In fact, that's already more than the international prefixes that we have today, right? So that's already a lot. But if it's still not enough for you, then with 64 bits, you can basically have like 300 zeros on either side of the decimal period. So that's quite incredible. So you can really shift the number left and right of the period. Does that make sense? For whom is that clear? All right. And the computers of today, the CPUs, they are really, really good at doing addition and multiplication. It's not that easy, right? Imagine you have to implement addition and multiplication of that. It's not trivial at all. But in fact, the hardware of our machines today, they are really, really good and optimized in order to actually be able to do that, right? Yes? The microphone maybe so that the people on Zoom hear you. Oops. Yeah, we need to use it, otherwise I need to repeat for the audience on Zoom. Go ahead.
I just wanted to ask, where does the readback mistake come from again?
So the idea is that you're going to input in some program. In our case, it will be SQL, but it could be any other language, could be Java and so on. So you might write down this in Java and then store it in some variable. And then you're going to continue your program and so on. And then you might want to print the content of that variable on the screen. And this is where you're in for a surprise, because you're going to get something that wasn't what you wrote originally. And the reason is that it got truncated. So there is a bit that is lost. Now your question might be, it's not just truncated, it's that there's actual digits here, 5, 7, and 6. And where does that come from, right? Maybe that was your question. It's because this part here in the mantissa, the blue part, that is on the right, it's ones and zeros. And in fact, here I wrote it for convenience is in base 10, right? Just for the screen. But in fact, it gets written in base 2. And so you have to imagine that when you store all of these bits right here, this is the weight of 1/2, 1/4, 1/8, 1/16, and so on and so on. So basically 0.5, if there's a 1, then you add 0.25 if there is a 1, 125, 0.0625, and so on. So you see that it's not just ones, right? Like you would have in base 10. It's really like negative powers of 2. And so what happens there, this here is an artifact of the fact that when you truncate in base 2. And these digits appeared because of these negative powers of 2 that kick in there when you truncate. Does it make sense? Right? It's really because of the discrepancy between base 10 and base 2. In base 2, it would just be like truncated. And in base 10, it gives you these weird things. Now, there exists a variation of this standard in also part of IEEE 754 that allows you to write the bits here in base 10, right? It means you really write, it's some weird encoding, weird way of doing it, but you really store that preserving the base 10 thing, right? For example, you could write every digit in base 10 on 4 bits, right? 4 bits are enough to give you 1 digit. So in that case, you would see an actual truncation without these weird digits. Yes, absolutely. It does. In fact, there are people doing PhDs on that precisely because of this. And people are trying to find ways to try, when you have a lot of operations, to try to tweak, because you can actually optimize things. You don't have to execute exactly in the way the program is written, right? So then there are optimizers that change the order, right? If you multiply A times B or B times A, it might also change, right? And so there are people doing PhDs and research on how to best optimize these things to mitigate that problem, because you're absolutely correct that this can be a problem, right? All right. Now SQL, because we are going to do it in SQL. Single precision is called real. Double precision is called double precision. In Java, it would just be double, and in Java, real would be called float. And then we also have this way of parameterizing the size of the mantissa, the blue part here. So I can say how many bits, I think it's bits that I want. So I can say float 24, meaning that I want a space of 24 bits for the mantissa. Float 53 means I want 53 bits. Now, this is the theory. That's what the standard says. But the implementations, in fact, very often, they will put anything between 1 and 24. They just take the real version, so the single precision version. And anything between 25 and 53, it will be just double precision. For PostgreSQL, of course, a different implementation of a SQL database might do something differently, but in that case, it doesn't actually respect your wish to cap the precision. It's really going to round up to how many there are in real and how many there are in double precision. This is non-standard, right? This thing. All right. But again, you're going to be using PostgreSQL, and this is what you need to focus about. So just know about this real and double precision, and know that this float blah, blah, blah is totally useless, at least with PostgreSQL. Okay. Now, there is a bit more in IE 754. It's that unlike these integers things, there are also special values. And the sort of special values we have is minus infinity, plus infinity. There is also none. That means, do you know what it means, none? Yes? Not a number, exactly. It means not a number. How do we get them? Well, imagine that you divide by 0. Then technically you get the infinity. Now you're going to tell me, okay, but which infinity, right? Because that's ambiguous. Could be minus infinity, could be plus infinity. Well, it turns out that in that standard, there is also the notion of positive 0 and negative 0. So 1 divided by negative 0 gives you minus infinity, and 1 divided by positive 0 gives you plus infinity. 0 by 0 would give you none, right? All right. So this is the idea. Now, that might be advanced because this might not be, it's more for computer scientists, right? But what if you compare numbers that are doubles? NaN normally in the standard is never equal to itself. If you compare something that's not a number to something else that's not a number, they are both nans, but the comparison of equality will still say they are not equal. But in databases, we do it a bit differently, and in particular in PostgreSQL, nan is equal to itself. Why do we do that? Because equality will be useful when we will group and aggregate data in tables. And in that case, we want to put the nans together. That's the reason. Higher than all of the other numbers. Why do we care that it's higher than all of the numbers? Remember that I told you about the set, bag, and list semantics, and in particular that the list semantics is implemented in PostgreSQL, and in SQL, you can actually sort the entries. So what happens if you sort a column that has doubles? None will just be considered higher. So if you sort ascending, you're going to have all the ascending numbers, then you're going to have plus infinity, and then you're going to have none, right? Okay, that's it for the numbers, right? So the integers, the arbitrary precision, integers and decimals, and then the floating point integers. Now we have the Booleans. That's the easiest. The Booleans, it's just two values. There's true and there's false. When you write down your SQL code, you can actually also use T and F or Y and N, like yes and no, on and off, 1 and 0. But this is, remember the lexical space? This is just the lexical space. It's what you would write in the SQL code. But as soon as it gets into the system, then it's just true and false. These are the two values. However, in the beautiful world of SQL, there is a third value. It's called three-valued logic, because we also have some unknown value. Sometimes it's called null. I'll come back to the nulls, or it's called unknown, depending on the context. But basically, it's just when you don't know. And you have also some sort of generalized Boolean algebra that takes into account unknown in addition to true and false, right? So you shouldn't be surprised that we will actually see these nulls and these unknown values in SQL, and we shouldn't forget about them. Now, this is probably the simplest list ever for my slides, because there's only one Boolean type, and I think this one everybody agrees on. It's just Boolean, right? Just a flag. We also call them flags, by the way, these things, because very often for parameter, you can activate or deactivate. So true means it's activated, false, it's deactivated, and you call that flags. All right. That was short, right? The Booleans, it's quite easy. So let's move on to dates and times. Then date and times, when people design new languages, they're always the ones that they forget. Like they think, oh, we have a question on Zoom?
Yeah, there's a question. Someone is asking, is null the same in Boolean as none before?
Null and null, or?
Yeah, basically, I think he's asking the difference between null and none, not a number.
Oh, the zero in here.
No, the null in Booleans and the not a number, maybe in the...
Oh, NaN.
Yes.
Oh, no, these are different. The null in SQL means you don't know the value, or the value is not there, right? NaN is a value, that is a double value, but it is a special double value that's not a number, right? So you really have to distinguish, this is not the same. This is not the same as that, none and null. Did that answer your question? Right? And is null equal to the empty string? No, I don't think so. If you have the empty string, that would not be the same as null. Null means really there is nothing. The empty string is still something. It's like the empty set in mathematics is something. It's a set, right? Does that answer your question? Okay, I'll come back to the nulls, right? Because they can appear anywhere, actually, in any columns, whatever the type. But I'll come back to this later. All right, I'm assuming that answers the question. All right, so dates and times. So the problem of dates and times is that many people don't take them seriously. I mean, when you think of programming, it's like, I want my strings, I want my numbers, I want my Booleans, and that's pretty much it, right? And then welcome to the real world of an actual company having this enterprise license of a SQL product, because in an actual company, you have to deal with dates and times and all these things. So the real world actually needs this. So this is why in any serious products of databases, you really also need to support date, time, timestamp. And also in the real world, it's a bit of a nightmare, because if you look at Java, C++, and so on, there is no really standard API. It keeps changing every time there is an update of the languages. They change again the way that dates and times are done and so on. So it's really, really, really tricky, right? But it's important. It is very important to support them. So let me briefly show you, because you can also have these in values in relational tables, the dates, the times, and the timestamps. So a date, in the Gregorian calendar, so the one that is used, at least here in Switzerland, so you have the year, the month, and a day. Like, what did I write? I meant 2023. I was a bit ahead of myself here, but 2023, October 6th, that is a date. It's a Gregorian calendar. You could, of course, imagine systems that support different calendars, right? So there are other calendars that are used in the world today, right? Okay, so this is it. Then you can have the hours, minutes, and seconds. That was a bit earlier than this. So in that case, it might be 10:31 a.m. And these are the seconds. And you can go all the way, at least in PostgreSQL, to microseconds. So you get 6 digits after the second. So this is a time, right? So dates is year, month, day. Then you have hours, minutes, and seconds. And then you get the timestamps where you have everything, the year, the month, the day, the hour, the minute, and the seconds, right? And that's it. Well, in fact, if you have to store this, this is not the way it's going to be stored. The way it is commonly stored is in terms of number of seconds since January 1st, 1970. It's kind of a convention, the origin of time. It's nice because that's also the origin of time of relational databases. So it's kind of nice. So this is here the display, the way that we abstract the actual value of the date, but inside it's going to be stored as a number of seconds since January 1st, 1970. All right. And again, I don't actually know if PostgreSQL supports other calendars. It's well possible. I think that there's languages like xQuery that do. There's, for example, the Islamic calendar that is lunar-based. That's also used. So yeah, you can have others. Then, now the types. So that's a long list in PostgreSQL. So date is when you put a date. Then you have times. The little numbers behind it is the number of decimals after the seconds here, up to 6. So in that case, we have just 3, so that's milliseconds. Now, what I haven't told you about is time zones. Well, you know time zones, right? They are the ones that make our life difficult when we have these Zoom meetings with people in other countries. So the time zone can also be part of the types you store. So you could actually store that together, saying this is like GMT plus 2 right now for here. And then you can choose when you store, do you want with a time zone or without a time zone, right? And you have to be careful because it can get tricky, right? So if you have a timestamp, for example, usually a timestamp would have a time zone because you need to know exactly the moment in time, right? Not just 2 p.m. without specifying the time zone. That would be less useful. So it's like a restaurant menu where you can just choose, right? Do you want the time zone? Do you not want the time zone? Do you want just the time? Do you want the timestamp? And so on. You just pick what applies to you. All right? Makes sense? Any questions? All right. Next, we have durations. Durations are not the same as time, right? Time is a point, a specific date or time or point in time. The durations are some interval that starts somewhere and stops somewhere, but we don't care when that is. We only care about the size of the interval. That's the duration. Now, there's also something tricky in there. So 2 years and 4 months, that's a duration. 3 hours and 14 minutes, that's another duration, right? But there is a trick, and I had this black line here between month and day, which is kind of some tricky barrier because of this. Because if I try to express a duration with months and days, then you see the problem here. 2 months and 30 days, 2 months and 31 days. What is this, right? Are we in February? Are we in March? You know, that kind of changes it. So this is the only one you need to be careful about because the number of days in a month can vary. So it's a good idea to avoid. Year, month, that's okay. There's always 12 months in a year. Originally, it's just because that's the number of times the moon does a full turn while the Earth orbits the sun. Days, hours, minutes, seconds, it's 24 times, 60 times, 60 times. So this is always an exact number, right? So this is it. And now, again, I'm giving you the restaurant menu of how this is done in PostgreSQL. You can specify what kind of interval you want, right? So there's the general one that accepts everything. Then you could say, for example, hours to seconds, right? So that many hours, that many minutes, that many seconds. The little number behind is again the number of like how many decimal digits do you want after the decimal period, right? Milliseconds, microseconds, and so on. I don't think it goes beyond microseconds in PostgreSQL and many others. All right, for whom is that clear? Okay, here we don't care about time zones, obviously. It's just a time interval. All right, and in some languages, I don't actually know if SQL does that, but there are languages that allow you to also add intervals to dates. So you can have a date somewhere, a duration somewhere else, and you can add the duration to the date to get a resulting date, right? That can also be extremely useful. We have a question, I think, on Zoom.
Yes. What is the worst which can happen? For example, interval seconds today, Would this give a warning, or could we end up with some false time?
You mean if you have more decimals when you enter it, like you have 8 or 9 digits, or? If there are more details here. Oh, second today. If you like the opposite direction, right? I actually don't know. Maybe you can test if you have a PostgreSQL instance and tell us in a few minutes. I don't know if it will allow you. Maybe it could be forbidden. That's my guess. Let's bet on throwing an error, but we'll get a confirmation from Bowen in a few minutes, right? It's really cool. We have a PostgreSQL running right here, so now we can answer in real time. By the way, it was very. I remember a few years ago that was funny, because I was giving this lecture here, and some of the students in the room had the PostgreSQL documentation open, so they were checking everything and spotting all of the mistakes. In fact, it's great because that's how I stabilized the slides and took a lot of them into account. But you know, I cannot compete against the internet, right? So if I do mistakes, just let me know, and I will fix them, of course, right? So we'll have in a few minutes an answer to whether it's allowed or not. Okay, durations. Now we have binaries. What are binaries? Well, technically it's images, video, audio, like whatever file you want, a PDF file, music sheets, and so on. Anything that basically you want to store in there. And in fact, you can do that. You can store files in a relational database. In fact, it can be very useful because, again, imagine you are hosting a WordPress instance and you're storing your text and your blog and the images that they are in there. That can be useful to actually have that in a relational table. And the types for this are very similar to the strings. You have binary 10 that is a fixed length, that's like char. You have var binary that is like varchar, that is a cap on the length. And then you have the variable length without limit, and you have blob, which is the sister of club, where blob is binary large objects, I think, and byte A, that's the non-standard way that PostgreSQL calls that. Somehow it's called byte A. I have no idea why, but this is what you can use. But again, it's the same as blob, right? Okay. Now I have summarized. That's not a full list. That there's a huge list of everything, but I think these are the most important ones for your reference that you might want to use. And again, the reason I wrote them in console character, like in this font here, is that these are the ones you can actually put in your Jupyter notebooks in the SQL when you create the tables, right? You can actually use them. In doubt, and this is what I do, just look up the documentation. PostgreSQL has a documentation, and it has a few pages on the types, and you can just look up it also explains the details of what behaves in that way. And if you have a doubt, you can just check it and see what happens. Okay. Now, all right. So that's the menu. That's the types. Any questions? Anybody? No questions. Okay. Does it mean you understood? Who is following? Who is understanding what I'm telling you? Okay, very good. On Zoom too? Do we have people on Zoom following us? Raise your hands. Quite a few. Okay, we have people following on Zoom. You didn't fall asleep. Very good. You're following. Very nice. Good. All right. So now we are going to move on to SQL instructions if we want to actually create our tables. Let's do that. Let's create our tables. So what can we do? Well, first it's called DDL. Do you remember what DDL means? Nobody in the lecture hall on Zoom, what does DDL mean? DDL, anybody remember? DDL, DML? Nobody? Libraries in Windows? No. Anybody? All the suggestions you have? Oh, yes, I got the libraries on Windows. It's DLL. I use macOS, so I'm not using a lot of DLLs. All right. DHL. All right. Ah, yes. We have a nice answer. Data definition language. That's exactly it. Thank you for this. So data definition language, and DML is data manipulation language. And so the data definition language, exactly, that's the language to create tables. I see in real time, by the way, I have the slides in the lecture hall, and I see the snippets of the chats that appear in real time. All right. So this is the DDL. We can create a table, we can modify a table, we can drop a table. So these are all the instructions we can give. So let's start creating a table. Of course, when I create a table, it's going to be empty, right? It's not like PostgreSQL is going to throw in some random data in there. It's just starting empty. So what we need to do is specify the name of the relational table, the attributes that we want, the name of the columns, and the associated domains that we want in there. Remember that here we have a relational table, we have relational integrity, atomic integrity, and domain integrity, right? I'm assuming all of that, and this is why I'm doing it in that way. If I didn't have these three constraints, that would be NoSQL, big data, and that's what we will do in Spring. But here, it's the beautiful world of SQL where I have these three constraints. So that's our hello world in SQL, create table, hello world table, that's how I'm calling it. And then we say name next. Name is the name of my attributes. I have just one column here, name, and text is the type. Remember that text, it's like a club. That's the unlimited size that I can have, right? Now, the first thing that you might have noticed is the uppercase, create table. I don't think it's actually necessary. I think in many implementations, you could also write this in lowercase, but somehow people are used to this. They are really used to writing the SQL keywords in uppercase. So I think you should do the same. It's a good idea to get used to it. I think it makes it easier to distinguish between the SQL keywords and your own names. For example, create table, you know that's a SQL keyword, and hello world table and name, they are lowercase. So you know that these are these are the attributes you come up with, and the same for the types. All right, how many columns do I have in this table? One, yes, I saw fingers. All right, one, and how many rows? How many? 2, 0, no. So if you count, it depends technically. If you count the header, you're going to have the headers and the type, so that would be 2. When we count, very often, especially in the exam, when we count rows, we really mean the actual data rows, right? So this would be in that case, how many data rows? 0, exactly. All right. Now let's do another one with 6 columns. First name, middle initial, last name, birth date, scientist, passport, scan. This is what I get. And I have the types that are also specified here, varchar 30, char1, and so on. This is what I get. I don't have any data, again, 6 columns. Now let me explain what I'm doing here, the way I draw. So I try to use the same colors. It might not always be the same. So here, these are my headers, the purple names. Here, these are my domains in yellow. And here I added something that I didn't do before. It's the name of the relational table that I add here. So here it's persons like this. And I did the same here with hello world table, name in here and text in here. So that's it. Now I'm a mathematician technically, so we need to look at the corner cases, right? It's like the vector spaces with 0 dimensions. They actually exist. So can we try to create an empty table that will have no column at all, right? Yeah, I'm not sure it's very useful. There's probably only one table that looks like this with 0 columns and 0 rows. Well, technically, you could also have with one row that has an empty map. That would technically be 1, 2. But basically, you can do it. You can put it in PostgreSQL, and that's what you get. All right, but it's the sort of things that I add because we can to it, because that's not really important. All right, now can we drop a table? Because I create it, now it's in the system, can I drop it again? then all you need is the name of the table, and you just say drop table, uppercase typically if it's the keywords, drop table, hello world table, and that goes away. That's it, drop it. What happens then, you might ask me, if the table does not exist? Well, obviously you're going to get an error that it doesn't exist. But if you don't want the error, and that's actually very convenient if you create scripts that automatically populate a database and you want the script to be idempotent, meaning that you can execute it again and it should work if it exists, but also if it doesn't, then you have this drop table if exists, table that may or may not exist. If it exists, it's throwing it away. If it doesn't exist, it does nothing, right? Okay, so now I just gave you the superpower to create and to drop tables. Now we are going to populate them because it's more fun if we have data in the tables, of course, right? So how do we insert records or tuples or maps? How do we update the tuples and how do we delete the tuples? This is called DML, and DML means, I'm sure on Zoom they will have the answer. In the lecture hall, anybody DML? Yes? Data manipulation language, exactly. That's what DML means. This time the lecture hall one. So this is DML because it's not about the metadata of the table, it's actually inserting data in there. So let's say I created this table before that has one column that is of type text, and I want to insert a tuple in there with the value Einstein. I can, and I'm going to end up with this relational table that has one record in there, Einstein in the column name, right? That's pretty much it. Now, technically, remember, in the theory, that's technically a map, right? I'm mapping name to Einstein in that tuple, but in that case, in the query, I didn't say it. Why? Because there was no ambiguity, right? There's anyway only one column, and I'm saying Einstein, so it just puts it in there. Now, if I don't like this ambiguity and I really want to be thorough and say the name, I can add it there, right? Questions? I see raised hands. Yes? Maybe the microphone way over there.
Does it already come with, what is it called, like a PID, or how did you call it?
Oh, the ID, the primary key.
Yeah.
No, it's your job to do it. And I will also show you how.
When you put in Einstein, it's not true. And
so let me try to interpret your question. Are you asking if name is automatically a primary key, or if it adds a colon for that?
Like, does this come like with already having like
So in some systems, like MongoDB is an example of system that does that, that when you create collections, it automatically adds an ID. I think in the case of PostgreSQL, it doesn't. You really have to explicitly add the PID colon in your schema, right? And you can add that it's a primary key. Was it your question? Yeah, all right. We have another question right here. Maybe if you can throw the microphone gently. Yes, awesome, go ahead. The quotation around Gödel, right? I think if it's numbers, you don't need it. If it's a number, you would just write the digits in there, right? And this is highly dependent on the software that you're using. So the way that it maps, I will show you, for example, binary. There is an ugly way of putting a few letters before the quotes and so on. But to answer your question, this is for strings, and in general, you might not need the quotes depending on the type, right? Did that answer your question? Right? Any other questions? No? Zoom questions? All right. Okay. And now, as you noticed, Einstein is still in there. That's because PostgreSQL keeps track of all of this, right? Your table has a life. It persists on the disk. You can even shut down your computer and switch it back on. It will still be there. That's what a database system does. You had one, or somebody has a question on Zoom?
Yes. What's the order of added entries? Does it append at the end or pop in the front?
Good question.
And is that always the same?
Okay. Good question. it's a Yin. I think that's the correct German word for this. So technically, PostgreSQL supports the list of record semantic, and the order is important. However, there is a small thing to understand. If you do not specify an order in your query, like we'll see actually in probably in 3 weeks from now how to query things, and there is a way in the query to specify an order. It's called the order by clause. If you do that, then there is the order that you're asking PostgreSQL. But in that case, we are not specifying any order, right? We are not saying anything. So technically, when you don't require an order, you've basically delegated the freedom to PostgreSQL to do whatever it wants. So there is an order, but that order is basically the free choice of PostgreSQL. That's it. Now, PostgreSQL is actually using that free choice wisely because it's going to pick the choice that is the most efficient in every context. So this is why you might see some shaky order in the sense that it might not be the same order every time, or it might vary. This is just because since PostgreSQL, if you don't specify an order, does whatever it wants, then it's free to pick whatever order it wants. But there is actually an order in the system. Okay. Did it answer the question? That was a Zoom question, this one, right? Did that answer your question? Yeah. So specifically on this one, in that case, it's so simple that I assume that what's going to happen is that it will put Einstein and then it adds Gödel's after that, right? But there could be cases once your database has grown and it takes a lot of space on the disk and you have deleted entries and there are blanks at a few places, it might be that it adds new entries in the blanks just to optimize space. So this is why you can never be completely guaranteed that it's always added at the end, right? For example, imagine that I remove Einstein. I will show you how to do it next week. Imagine I remove Einstein. What is it going to do on disk? Well, it could remove Einstein and then move Gödel up one level, right? And change the way Gödel is stored. And that would be inefficient. It's much more efficient to delete Einstein and mark it as deleted and to keep Gödel where it is, right? Where he is. So in that case, if you add, after deleting Einstein, you add, I don't know, Ramanujan, then probably you will put it where Einstein was stored, right? And then you would end up with Ramanujan Gödel, but you might also end up with Gödel Ramanujan, depends on the implementation, right? But this is the physical level. Here, I'm not talking about the actual model and so on, because in the model, it's basically setbacks and lists, and that would be specified. This here is an implementation detail, right? Did that answer your question? As a complement, I mean, that's a complement of answer. If it times out, then that's a yes. All right. Okay, and I'll do that next week. This is when you want multiple rows at the same time with multiple columns. I'll keep it as a cliffhanger for next week. So in order for you to control my speed, as I promised to you, I want to check how much you understood. That gives me some sort of compass for the speed. Where is this? It's right there. So tell me how it went.
And regarding the previous question on the second to day or day to second, so the SQL parser won't even allow you to write something like second to day.
So it's an error.
Yeah, it's an error.
Okay. Yeah. So
the parser will.
Question. Yeah. That was a Zoom question, I think. Let me show live, because of course there's no reason to hide this. Wonderful. Okay, perfect. So I'll keep the speed, but again, I can accelerate, I can slow down. I'm just going to adapt with how you're following. Thank you very much, everybody, for attending today. Thank you for attending on Zoom, and I'll see you next week. Enjoy the exercise session this afternoon and on Monday. Thank you very much. Goodbye.